Good afternoon, everyone. My name is Luay Nakli. I'm the Dean of the School of Engineering and Computing here at Rice University, and I want to welcome all of you to the Raleigh Johnson Lecture Series, which is an annual lecture series that we have in our school. This lecture series is established in memory of our alumnus, Raleigh White Johnson Jr., also known as Bill. Bill served in the U.S. Navy during World War II and went on to graduate from Rice Institute in 1949. For those of you who don't know what that is, this is Rice University, used to be Rice Institute, with a Bachelor of Science degree in Chemical Engineering. As a student, he was a member of Jones Residential College. Shortly after graduation, Bill stepped into a leadership role at Raleigh Johnson and Company, a company founded by his father in 1931. The company represents high-quality, synergistic food equipment lines and has 8 factories in Texas, Oklahoma, and Louisiana. Beyond his professional life, Bill was deeply committed to the Houston community, serving in numerous boards, including the Texas Medical Center. Rice was also central to his personal life. He met his wife Marjorie here, and together they built a lasting Rice legacy that spans generations of owls, including grandchildren, Eastman Landry and Ellis Landry Tyrone, both engineers from our school, and Richard Colvin Jr., who received his MBA, and his nephew Stephen Arnold, 88. Through his estate, Bill established the endowment that makes this series possible, creating opportunities like this one for our community to engage leaders shaping the future. And we are very honored today to have members of the Raleigh Johnson family here. Please join me in welcoming them. We are very grateful for the Johnson family and for this wonderful gift that allows us to give this lecture series where we bring speakers and scientists and engineers who are changing the world to speak not only to the Rice community, but also the Houston community as well, and this is open to the public. And with that, it is now my pleasure to introduce today's speaker. Partha Ranganathan is Vice President and Technical Fellow at Google, where he is driving next-generation computing systems for the AI era. He has pioneered innovations that touch billions of people, including widely adopted ideas across mobile and cloud systems. He has published more than 100 papers, co-authored the widely used textbook, Data Center as a Computer, and a co-inventor of more than 125 patents. His contributions have earned him numerous awards, including the top 35 young innovators in the world by MIT Review. And he's also elected as fellow of the IEEE and ACM fellow as well. One other thing is that when I travel as dean, I meet with alumni. I'm always looking for qualities in our alumni, and I love to come back and we talk about them. One thing that is not typical to see when we meet with alumni, and something that Partha is officially certified for, he's a rock star. He's actually was a top 15 enterprise technology rock star by Business Insider. So, yes, he's a rock star. Partha is also a recipient of the Rice University Outstanding Young Alumni Award, as well as IIT Madras Distinguished Alumni Award. And then there's another thing interesting about Partha, that typically, when we look at computer scientists and computer engineers, awards we look at are some known in our domain, but Partha is also an Emmy Award winner. So he's one of our Emmy Award winners in the school. So this lecture series is not only speakers from our school. It is actually for speakers in general that are of interest to the community, but it's always especially proud for me when we introduce one of our alumni as one of these distinguished speakers. So I'm very, very proud to introduce to you Partha Ranganathan here. But before I get him here, actually I want to say one thing. If you look, he has a red backpack with him. He showed up to campus with a red backpack. And it is from University of Maryland. So I don't know why he came up with that. So I have
Thank you.
So with that, I turn it to Partha. At the end, we will allow about 10 minutes for questions and answers. And please take a picture of the QR code if you want to submit questions, because in this QR code, you will submit questions. And then at the end, I will choose some of these questions to ask him so that we manage to ask as many questions and to be as diverse as possible with the questions that we ask. Okay, thank you very much.
Cool. Thank you very much. Okay, so with that introduction, it's a little tough. So first of all, the Maryland bag, it's red and bright, and I have a habit of forgetting things where I go, and so I just like to have something that is very visible. And it was actually, I gave a presentation on the future of AI, some of the comments I'm going to make to the regents of University of Maryland as well. And I'm so delighted I get to kind of talk about these comments here as well. So it's a pleasure to be here. It's amazing to see such a full audience here. This building has very special memories. This was where I defended my PhD thesis. It's a little intimidating to see some of the professors that I taught here, but it should be fun. So very quickly, how many people here are students? Oh, wow, good. I'm glad there's so many students here. How many are faculty members? Oh, equally large number. Okay. How many people are from outside Rice? Okay, I'm glad. Welcome. So I hope you enjoy the talk. My talk is titled From Unicorns to Centaurs, Powering the AI Moonshot. And I was told that a good talk is kind of like the sun. It's both a light source and a heat source. A light source because it illuminates, and I'll talk a bunch of trends that hopefully shed some light on some of the trends going on in the world. A heat source in the sense that it's a little provocative and it makes you think about what's going to happen as well. So with that as the context, my talk is going to be structured into 4 parts. The first part is kind of a prologue, and I'm going to talk about the era of intelligence that we are in. I'm going to talk about AI and the trends and the opportunities ahead for us. And then the next 3 parts are a little bit of the past, present, future. And I call them unicorns, centaurs, and cyborgs, and you'll see why in a minute. The first part on unicorns, I'm going to talk about systems for AI. And I'll talk about how we are building some amazing silicon accelerators that power the intelligence revolution. And then the second part, I'll talk about AI for systems. And I'll talk about Centaurs, which is human-AI collaboration to kind of take the next wave of infrastructure. And then towards the end, with cyborgs, I will speculate a little bit on where we are going with the whole AI era and see where things are going. Okay? And again, I will be remiss if I didn't say that a lot of this work is based on a lot of amazing collaborations. My colleagues at Google, of course, but also collaborators in academia and industry. So real shout out to all of them as well. So with that as the context, let's talk about the intelligence era. So I don't think anybody is going to be really surprised when I say that AI is the space race of our era. And particularly given the Artemis things now, I think this is a very apt metaphor to look at. And if you think about AI, it's everywhere. It's fundamentally transforming all aspects of our life. In the consumer app, each one of these apps at Google, each one of them have 500 million users, and every one of them has been transformed by AI in the past year. Whether it's search with generative AI summaries, or whether it is Google Photos, where you can do some amazing search, or Gmail, which writes your email for you, or YouTube, or Android, or Chrome, every single one of them has been transformed by AI. My favorite, video and image editing with Nano Banana. So how many people use AI to kind of make any images here? At least the students hopefully are having fun with that. Okay. So what I thought I would do, just as a fun warm-up to the talk, I thought I would show you my prowess at AI-edited video. So let's see the first video here.
It's so great to be here with all of you tonight. I'm excited to share some big news.
Okay, so my kids tell me that the AI Partha is much better than me. Apparently, he smiles a lot more, so I'm practicing smiling, but I can't kind of do the whole... But when you think about the fact that this particular video snippet was generated with that tiny image and that tiny prompt that I gave, it's just magical. And so really supercharging how consumers interact with technology. And it's not just consumers. If you look at enterprises, so at Google Cloud, we've seen in the last year a fundamental change in how people are using AI. It's no longer people just kicking the tires on AI. There are multiple use cases where AI is fundamentally providing a good return on investment. So it has to do with scenarios where you process large amounts of data. It has to do with scenarios where you want to have a natural interface, so you have something like a chat-based agent, or it has to do with things where you're looking at the generative aspect of generative AI, developing marketing collateral and so on and so forth. But one of the places where it's particularly interesting is this notion of agentic AI. And so with one click of a button, you can do a lot of coding. So how many people here do vibe coding? I saw somebody with a T-shirt which said, I love vibe coding here. Who was the person with the T-shirt? Okay. They are too scared to admit it here. Okay. Okay. And the reason I have this book here is not because I am shamelessly plugging my book. You should read it, by the way. But the first student who asks a question, I usually end up giving them a signed copy of the book. So I do like to make it interactive. It's a small enough group here that we should kind of think about it that way. So agentic AI, whether it is coding agent or security agent or customer agent, data agent, amazing stuff there. But more interestingly, AI is also fundamentally changing science. So how many people here know what AlphaFold is? Oh, good. Again, Texas Medical Center, I guess. AlphaFold, again, I didn't know this, so maybe I'll explain it a little bit. So we all know proteins are a sequence of amino acids. Yes. But it turns out that the way the proteins fold, the structure of the proteins, are super critical to understand how the protein works, understand how you can use it to solve disease, and so on and so forth. And so protein folding is an incredibly hard problem. And typically, it takes like one PhD student 5 years to kind of go do wet lab and do all these things and figure out how one protein works. And what we did with AI is in a click of a button, we were able to identify the protein folding for 200 million proteins in the world. 1 billion hours of research in one click of a button with AI. Incredibly powerful, and that's why this got the Nobel Prize for two of my colleagues for a Nobel Prize for chemistry. But it's not just AlphaFold. So we have subsequent sequels to AlphaFold 3 and so on, which looks at all materials. There are more biological sciences, alpha genome, alpha mesons. There is earth sciences. There is weather forecasting, using AI for weather forecasting. There's material sciences, using AI to figure out nuclear fusion. There is computational sciences, AI for AlphaEvolve, AI for co-scientists. You have virtual worlds that you can build with AI. You have robotics with AI. So much so that I often joke that last week was an amazing year in AI. And there are weeks when this is not that far from the truth. So lots of amazing stuff in AI, but you might be wondering, well, Partha, you said you're going to talk about infrastructure powering these AI moonshots. What does all of this have to do with infrastructure? And so the key thing to think about is that when you think about these AI models, we started with Google had this thing called the transformer model. How many people here have read the original transformer paper? Okay, again, I see a good chunk. So the transformer paper was the prelude to all the work that we have here. And starting from the transformer paper to where we are today with Gemini 3.1, we went from millions of parameters to now trillions of parameters. And so to quote my favorite superhero, with great models comes great computing. And so what you see here is that the picture basically shows how model sizes have been growing, and correspondingly, the picture on the right shows how computing has been growing. And I want to make a quick observation here, right? So if you look at the data there, and you look at the last 5 years of model growth, or last 10 years of model growth, roughly factor of 10 every 2 years or so, right? Which basically means a factor of 2 or so every 3 months. So that's how fast AI is growing. Now, if you look at the computing that powers AI, we have something called Moore's Law. So I'm sure everyone knows what Moore's Law is. Okay? So Moore's Law is basically what powers all of our computing infrastructure, and it's a law which says that computing performance doubles roughly every 2 years for the same cost. So that has been kind of key to the entire computer industry, underpinning everything from self-driving cars to small miniature phones and everything. Computing doubles every 2 years. The demand for computing is doubling every 2 months. So that difference in exponential is a huge problem. And then to make things worse, Moore's Law is slowing down. And again, I can go into a lot of details on the physics on why technology scaling is slowing down and so on. But what that means is every single metric that you care about, whether it is performance, whether it is performance per dollar, performance per watt, whether it is memory, whether it's storage, whether it's computing, Everything is plateauing. So this problem is really what we want to try to solve. And so the metaphor, again, going back to the moonshot metaphor, if I think about my colleagues in AI as space researchers exploring brand new worlds, people like us who design the computing infrastructure are the ones designing the rocket engines, and we need to really design better rocket engines. And so how do we do that? And so that brings us to the second part of the talk, which is unicorns. Oh, look at that beautiful owl. So I told you I'm very proud of my video editing skills. And so unicorns are basically this notion of vertically integrated accelerators. And at Google, we've been incredibly lucky to have a front row seat in how we design systems for AI. And the idea that we have been adopting is this notion of cross-stack, cross-disciplinary systems innovation. So what do I mean by that? So we start off with building chips. And we build custom silicon chips designed for machine learning AI workloads. And the reason we do that is when you kind of take something and you build hardware specifically targeted to a specific workload, you can make it very efficient. You can make it very efficient in transistors, make it very efficient in area, make it very efficient in power, make it very efficient in cost. And so we did that. And so we have something called the tensor processing unit. How many people have heard of the TPUs here? Again, most people know that, good. So TPUs, we are now in our 8th generation. And the TPUs include a lot of innovations. We did custom numerics, which basically said, hey, we're going to kind of play around with efficiency there. We built custom accelerators for matrix multiply. We built scores. We built a bunch of things there. And that has been very nice. But then on top of that, we take all of the silicon and we wrap it into systems. We start thinking about how do we do efficient networking. So we talk about using fancy mirrors to kind of do optical topologies that are reconfigurable that allow you to do some really large systems at scale. We put things in liquid cooling. And Google is the first company on the planet to have multiple gigawatts of liquid cooling distributed across the world. And liquid cooling gets you an order of more efficiency. We think about power. How do we have sustainable green power? And how do we think about things like medium voltage and so on? And then on top of that, all of that goes into the lowest level of the picture on the left here. And then we start thinking about performance optimized hardware. We think about compute. We think about storage. We think about networking. And then we co-design that with the rest of the software stack. We think about co-designing that with the compilers, the XLA compilers or the Kubernetes, PyTorch, and so on. And then we co-design that with the cloud schedulers. And that whole stack, Google calls it the AI hypercomputer, that becomes the bottommost layer on the picture on the right. And then we co-design the AI hypercomputer with the models, whether it's the Gemini model or the Gemini Flash or Gemini Pro. And then we co-design that with the agentic garden, Vertex AI, and then all the way up to applications. So this co-design, all the way from chips to systems, from systems to platforms, from platforms to solutions, is incredibly powerful. And for Google, over the years, we have gotten anywhere from factor of 10 to a factor of 100 improvement in any metric that you care about, whether it's performance or performance per watt or performance per dollar. In efficiency, it has served us really well. And not only has it served us really well, it has also served as a template for an entire cottage industry of new innovations adopted widely in the industry, both by big companies, but by also a lot of billion-dollar unicorns. And for those of you who don't know, the Silicon Valley term for unicorn is basically a startup that is worth more than $1 billion. And now we have decacorns, which are $10 billion and silly numbers like that as well. But a lot of really, really nice innovation there. And so when you think about what has been the common theme here, it is this notion that you're not thinking about hardware in isolation, you're not thinking about software in isolation, you're thinking about co-design. You're thinking about hardware, software, co-design, and you're really fundamentally rethinking the interface, the harmony between hardware and software, and that's served us really well. So now, this is what we've done so far, and as I look ahead, there's tons and tons of opportunities. You can think about new data centers, where you think about modular data centers, robotics in the data center, mechatronics in the data center, new distributed systems, new servers, disaggregated servers, and so on, new chip accelerators. So the Emmy Award, just in case any of you didn't get it, it's a technical Emmy Award. So I don't sing like Taylor Swift, so don't expect anything like that. So the Emmy Award was for building an accelerator that transformed how video gets generated. And so whenever you do YouTube or any YouTube TV, it was infrastructure there. So there's a lot of work to be done in accelerators. And all of these, again, all these innovations, there's tons of stuff to be done there. But what I thought I would do is to really talk about 3 vignettes here in terms of really big opportunities for us to think about. So the first one is around efficiency and sustainability. And so many of us, if you're reading the news, we hear these things about like AI is going to be transformational, but AI is also going to blow up the planet because the carbon footprint is very high. We don't have enough power in the grid. AI is going to be true transformational. And all of this is very valid, but it is not as dire as it sounds because there's tons of opportunities for how we can improve efficiency and sustainability. And so we can start with more models. So when we think about efficient AI models, you can do a lot to optimize for stuff. So for example, at Google, the first year we introduced generative AI summaries. From the time we introduced it to 12 months later, we had improved the model efficiency by 90 to 95%. So that's a factor of 10 to 20 improvement in efficiency. So model design, there's a lot of opportunity. Infrastructure, the TPUs that I talked about, they are incredibly power efficient, almost a factor of 10 to 20 more power efficient than equivalent general purpose CPUs. And then finally, in terms of efficient emissions, there's a lot of really nice opportunities that we can look at, all the way starting from more carbon efficient fuel sources to kind of thinking about more efficient distribution of power and so on. And so the one example I want to give here, which is again a classic example to prove my point about co-design, is this project at Google that we call Project Smoothie. So what this project is basically the picture shows how power is pulled from the grid for a really large AI cluster. Now, Google has been designing large systems for 25 years. So we think we know how to do YouTube and Gmail and search. These are really huge systems, millions of servers running together and so on. But AI workloads are fundamentally different from classic hyperscale workloads. And the reason AI workloads are different is they are what is called bulk synchronous workloads. And so bulk synchronous workloads basically go up at the same time and go down at the same time. So you have training, you have pre-training, and so on and so forth. And so when you do that, you have almost hundreds of megawatts of power variation that you go to the grid. And that is not very friendly to the grid because the grid now has to kind of plan for these huge power spikes and so on. But it's also not good for your servers because reliability gets affected when you have these thermal differentials and so on. And so what we did, again, going through this notion of co-design, we kind of went through the system all the way. We said, hey, the chips need to have hooks for management. The compiler needs to have hooks for management. The model needs to be able to distribute your load. And by doing this at every layer, you went from the blue line to the purple line, where you literally smooth the power load. And a lot of really, all the problems that we talked about went away. But more interestingly, we now have this new knob called demand response, where we are controlling the demand to the grid. And what that does is it allows you to think about new opportunities where these large data centers, instead of just being consumers from the grid, they can start participating in the grid. So you can have microgrid controllers, you can have renewable energy sources, you can have on-site power generation. And so it opens up a whole bunch of new opportunities for how we can innovate in terms of environmental sustainability. So when you go back and somebody asks you, maybe your grandmother says, is all this AI stuff going to blow up the planet? You should now be able to tell them, no, Partha told me there's a lot of opportunities still left, and we are going to solve all of those, especially for the students there, right? Okay, so the second thing I want to talk about is this notion of agility. And when I talk about agility, if you think about how data centers are built, there are multiple time constants in a data center. So typically, when I need to build a data center 15 years earlier, I need to kind of provision the land. I need to provision the power and so on. Hardware takes multiple years to do. Deploying these takes multiple years as well. And so these are really, really large time cycles. And in contrast, software, when you think about AI models, they keep coming up with new updates every 6 months. I talked about how every week feels like a year in AI land. And so if I'm a hardware person designing the hardware that runs all these AI workloads, if I'm designing hardware today, I need to think about what are the next 6 advances in Gemini that's going to happen, Gemini 4, 5, 6, 7, 8. And if anybody can tell me that they know exactly what is going to happen to AI models in 3 years, I'd be very interested in getting their stock market recommendations or something, right? So it's just impossible. And so what we need to do is to really start thinking about how can we design systems to be agile and fungible. And what that means is we need to start thinking about modularity and manufacturability as first-class design considerations. But we also need to start thinking about standards and ecosystems and so on. And then the last part I want to talk about is how do we do co-design for capability. And what I mean by capability is when we think about designing accelerators, so how many people here identify with designing hardware in your PhDs or your job? How many people are hardware people? I see Professor Cavallaro raising his hand tentatively. So, okay, so a few of you. And so for the people designing hardware, the way you design hardware accelerators is you draw a pie chart of where do we spend all our computing cycles, and you take the biggest chunk and say, hey, I'm going to build an accelerator that makes it go faster. Okay, kind of makes sense. But every single accelerator that I have worked on at Google that has been successful not because we focused on efficiencies. It's been successful because we focused on capabilities. What do I mean by capabilities? So it again goes back to when we first designed our TPUs, AI workloads were not a huge fraction of the fleet. In fact, they were a single-digit fraction of the fleet. But what we realized was that designing an accelerator unlocked a new capability that wasn't possible. And the thought experiment we did was if every single Android phone in the world did 3 minutes of voice recognition, we realized we had to quadruple how much capacity we had. We had to build 4 new Googles. And so we said, hey, that's not things, we need to build an accelerator. Same thing with that video accelerator that I talked about. The video accelerator was good because it accelerated transcoding, and so we saved a lot of money in terms of making it go faster. But the capabilities it enabled, 4K video, 8K video, live video, streaming, YouTube TV, cloud gaming. So if there's nothing else that you remember from my talk, and you are in the business of building hardware, remember capabilities are much, much more important than efficiencies. And so what that means is, if you think about where we are going with new ML workloads, whether we are thinking about new sparsity in the workloads or omnimodality in the models or new autonomous recursive self-improvement, distillation, and so on, tons and tons of opportunities for us to be looking at new capability as well. So those are kind of 3 main vignettes I wanted to talk about. But if you look at where we are going, there's tons and tons of new model scaling that needs to happen. And you can see these numbers. These are not percentages. We are seeing orders of magnitude improvements, orders of magnitude increase in the demand for computing. And so if you go back to this picture that I talked about, I said, hey, Moore's law is dead. And what we did with building these unicorns, building these custom silicon accelerators, is we got a bump up. And we went on a much better exponential. But we now need to kind of figure out, for all this demand on AI that's coming up, how do I get to that stuff? And so to kind of give us the answer to that, I thought I would invite a special guest. And I asked the special guest to tell me the answer in 1 word.
AI, generative AI, AI is AI. It uses AI to bring AI.
Okay, so for those of you who didn't know, this is Sundar Pichai, who is the CEO of Google. I often joke, Google is the only company whose CEO has the name AI in his last name. But as Sundar very kindly pointed out to us, the answer is AI, right? And so again, going back to if we are building the rocket engines that power our AI researchers, shouldn't we be using the rocket fuel and rocket engines ourselves as well? And so what I want to talk about is this next part. Oh my God, I'm so proud of my videos. Okay, so what I wanted to talk about was these Centaurs. So why Centaurs? So how many people have read the book Deep Thinking by Gary Kasparov? 1, okay. How many people know who Gary Kasparov is? Okay. How many people play chess? Okay, so this isn't as bad as I thought. Okay, so Gary Kasparov was a chess champion, and he got defeated by an AI machine. And this was like 15 years back. And he wrote this book with a lot of angst on, hey, is AI going to take over our jobs? And one of the things he realized is that the championships were not going to be won by just the best AI or the best humans, but average AIs working with average humans were the ones who were winning these things. And he dubbed them Centaurs, which is this notion of human-AI collaboration to kind of do that. And that's a term that's been used in the industry quite often. And what we have seen is that this is an incredible opportunity for us to get the next wave of performance for systems, whether it is all the way at the circuit level or the architecture level or the systems level or the language level or the algorithm level. And so what I want to do is spend the next 10 minutes kind of giving you vignettes of how we have been using AI to advance systems. And then again, I'm going to up-level it to kind of talk about a few key examples of what are the key opportunities here, and then we'll go from there. Okay, so let's start with VLSI circuits and so on. So Connor, this is where things get a little bit more technical. I have jokes for you there, so if you want to, you can just look at the joke as well. So my kids tell me I have lots of bad dad jokes, and you'll see those in the next 5 slides. So first thing is chip design. So it turns out chip design is an incredibly hard problem, and there's a problem called place and route in chip design, which is basically how do you put the blocks on your chip. And it turns out it's a combinatorial explosion problem, and it's a very similar problem to how you use AI to play chess or how you use AI to play Go. Except in chess, the combinatorial space is 10 to the 100, 1 followed by 100 zeros. So you have to do so much. In Go, it is 10 to the 400. In place and route, it is 10 to the 9,000. It's an incredibly complex problem. But what you see is that AI, and the pictures on the right show that, AI can do as well as a human. And not only can it do as well as a human, instead of the human taking 8 person weeks, it takes 24 hours. So incredible transformation in using AI for chip design. Another example is to do AI for memory design. So all computers have memory DRAM to do that. And so if you look at Google, and that's what the picture on the left shows, if you look at Google as one big computer, 30 to 50% of the time, I'm stalled waiting for something to come back from memory. So for every $1 I spend at Google, 50 cents goes down the drain because I'm sitting there twiddling my thumbs waiting for something from memory. Anyone care to guess, anyone know how much money Google spent on buying new computers in 2025? You can throw out a number, it's not your money. So, I'm sorry? $1 billion. I hear billion going once. 5, no. So last year, Google spent $80 billion buying infrastructure. And this year, we guided the street to saying we are going to spend $180 billion on new computers. And so if I lose 50% of my money waiting for memory, that's not a good place to be in. And so we asked this question, when you use Google, you do autocomplete. So you search for R and I, and it says, hey, are you searching for Rice University, right? And so we asked this question, when I'm getting memory access A and B and C, can you automatically figure out that D, E, and F are coming there and bring it to your local cache so that instead of spending a lot of time going to memory, you get the answer right away? And it turns out it works beautifully. And so that's what that picture shows here, is not only do we do really better compared to the best solution before, but that picture tells you that we can now actually understand semantic information of what these memory access patterns are. You can say, hey, you know that particular big cluster, those are memory access patterns where you're kind of doing sequential access. You know that particular cluster, you're doing pointer chasing. And that makes the programmer more effective as well. You can also use AI for data center design. So I talked about liquid cooling and so on, and it turns out you can really get more efficient there. You can use AI to write better code. And one of the things that we often talk about is a lot of people use AI for vibe coding, right? And so people can use AI to make coding faster. But the work we did was to make the code go faster. So the output, so we looked at the program and we said, hey, look, if I have 100,000 correct answers for a problem, let me draw how the execution time for all of those. And what we realized was that different people did different answers and they did different tricks and so on. And you could reverse engineer and figure out the various tricks people used. And you could say that, hey, you use combination A and B and you use combination C and D and so on. But then what was really powerful was that the difference between the best performing coders, the code that ran really fast, and the average was a factor of 2 to 4. So again, going back to if Google is spending $100 billion on infrastructure, and I can take all the ideas from the smartest programmers who get really fast code and apply it to everybody else, I get a factor of 2 improvement in efficiency. So that's amazing. And same thing now with, we can also think about AI for co-design, and we did a lot of work there as well, and it turns out AI works really well as well. And again, you'll notice that now the common theme again is co-design, but this time it's not hardware-software co-design, it is AI systems, AI human co-design. And again, you have the same notion that the next era is going to need us to cross disciplines, cross communities, and work together. And so I often joke, is anybody live tweeting here? I see people taking pictures, but if you're live tweeting, you can always say, Partha says everything tastes better with a sprinkle of AI. And it's true whether it's hardware, whether it's systems, whether it's operations, whether it's security, everything works really well. But I wanted to quickly talk about maybe 3 opportunities that we have here. One is responsible AI. And so again, I don't want to have you leave assuming AI is a panacea for everything. So I talk about the 3 H's, hate, harm, hallucination. So we need to do AI very responsibly. The second is this notion of systems for AI. And so what you want to think about is how do you go beyond just thinking about models to modeling? How do you build the harnessing, the scaffolding that needs to happen? And then the third is you really need to think about AI as a journey. How many people use AI to improve their productivity in some form? Everybody, oh my goodness. So I'll tell you a story here. So 8 months back, I wrote my first AI script. And I said, you know what, AI is amazing, and I have so much to read, and I don't read all the amazing things. Benam writes amazing stuff. Louis posts on LinkedIn all the time. I don't get to read all that. So I'm going to write an AI agent that's going to go look at everything and send me this beautiful newsletter in the morning that summarizes all the things I should be reading. It worked brilliantly. So at the first week, I was like, okay, I'm on top of everything. Benam, you can ask me any question. I'll ace my PhD defense, right? But then what happened is the week after, I actually regressed. And the reason I regressed is because I was getting so overwhelmed with all the information, I didn't have bandwidth to kind of handle all this extra information that was being thrown. And we see the same thing at Google. So you make coding go 10x faster, testing becomes a bottleneck. You make testing become 10x faster, documentation becomes a bottleneck. And so there is this notion that you need to look at the entire workflow, because if you just make one part faster, we all know this, if you make one part faster, there is something else that's going to get slower. So this notion that there is this thing called the 10x problem, where if you make one thing 10x, other things break. So you want to really think about the entire AI-infused workflow. And you also want to think about the same thing across hardware and software. You make hardware faster, you need the software to go faster as well, otherwise things don't work. So we spend a lot of time thinking about that as well. So that's the second part, which is this notion of thinking about AI for systems. And I've noticed that there's a journey that happens. We go from drudgery, which is basically using AI to automate grunge work. And then we go from drudgery to development, which is where we are with all the vibe coding and so on. And then we go to design and then disruption. And as you go to disruption, the industry has this term called cyborgs. And just like Centaurs was half human, half AI, cyborgs is also half human, half AI, but they are more finely grained, intertwined, and it's more blended division of responsibilities. And so the last 5 minutes or so, I want to talk a little bit about I even managed to get rice. And so I want to talk about what do we do in a world of cyborgs. And I want to give 3 examples again. I want to talk about agency. And the idea behind agency is, so far I've been talking about how do we model the messy world. I want to talk about how do we not just model the messy world, how do we influence the messy world. And so we have this work. How many people here have heard of Alpha Evolve? Not as many. Okay, so Google has this tool called Alpha Evolve, which is basically using AI to do reinforcement learning. So basically, AI becomes an agent that kind of works behind the scenes. And so again, I'll tell you a story here. Last summer, I had an intern from not Rice. I'm going to get another backpack for this now if I say where it's going from. He was from Berkeley, so 22 years old, first year PhD. And I told this kid, hey, look, I want to try out agentic architecture. And in computer architecture, we have these competitions that we run. And I said, pick any one of these competitions. There's cache replacement, branch prediction, prefetching. Try to see how agentic stuff works. 18 days later, he was world champion. 3 months later, he was world champion on all 3 of the championships. And so being able to use agentic architectures to do design space exploration is incredibly powerful. There were lessons we learned as well. So A, we learned that this is super powerful. B, we learned that it is incredibly hard to understand these. So I asked AI to say, hey, can you help explain what this is? Can you come up with names? And AI came up with, one of the things it came up was emotional cache replacement, psychoacoustic pattern detection. My favorite, astropsychic oracle plus cosmic ray shower. Who knows what that is, right? So understandability of AI is going to be super important as we go ahead. The second lesson we learned, I said 18 days we won the championship. We actually won the championship in 4 days, except it turned out it was wrong. The numbers were staggering, and I was like, okay, Nobel Prize, here I come. It turned out the AI model cheated. It saw that the simulator, very rightfully, the simulator was not modeling a certain aspect that didn't need to be modeled, and it went and pushed on that particular vulnerability, and it cheated. And so again, figuring out how AI works, super important as well. And so we can actually now take this to its logical extreme and say if AI is designing systems, we can completely reimagine how we design systems. And instead of taking $100 million, hundreds of people, lots of effort, can we kind of make this be weeks, tens of people, tens of millions of dollars? So we are working on this, and it turns out it's actually a very exciting but also solvable problem. So the next time I'm here, I look forward to solving more things there as well. Second is AI first research. And so again, Google has this thing called co-scientist. And what we have with co-scientist is you can ask AI to invent ideas for you. And so again, please go look at this. This is actually available for people to try that. Incredibly powerful. But what you can do with co-scientist, you can now go back to the stack and say, hey, look, as humans, we look at one layer of the system because we like to kind of block things. That's all we can model. You can come up with incredibly new ideas. So going back to these Alpha Evolve, the intern that I had, when you combine co-scientists with Alpha Evolve, you come up with some really magical ideas. How many people have heard of Move 37? Okay, a few people. So what Move 37 is a story where when AI was playing Go, and it defeated Sedol, who was the championship, the 37th move was an incredibly complicated move that nobody really understood. They thought the AI was kind of hallucinating. It turned out to be a brilliant move in hindsight. And a place like Go, where there is centuries, decades of innovation, having AI come up with a brand new idea was very interesting. And you can fully expect a lot of Move 37s in system design as well. The last point I want to make is around this notion of AI native innovations. So how many people know what that picture is? I actually say what it is, so I guess it's an easy question to do that. So this is a Ford Model T car. And what you notice is that the Ford Model T car looks a lot like a carriage. And so this is how innovation works, is the first time you kind of try to do something new, you just copy it into the new technology, whether it's digital or whether it's AI and so on. Right? Think about CDs. When you first had music go digital, you took CDs, you ripped it. And then what you did, you said, well, you know what, I'm going to kind of now have searchable, so you're going to augment it with the new technology. And then what did you do? We said, hey, you know what, I'm going to have single strong, I'm going to do streaming, I'm going to create business models, you're going to start kind of thinking about the technology first. And then where are we today? YouTube Shorts, TikTok. That is a format of media that is fundamentally digital native. And so you're going to see the same journey happen with AI, where you're going to do AI lift and shift, you're going to do AI augmented, you're going to do AI first, and then you're going to go to AI native. And so as an example of AI native, I want to end with this. Remember I said AlphaFold solved 200 million proteins. What did we do after that? What we did was we started solving problems like plastic pollution, antibiotic resistance, structural biology, malaria vaccines, drug resistance, the long tail of diseases, and so on. And so incredible new opportunities got unlocked when we started using AI to do that. And so if you think about science, science has gone in these various epochs. So you had the first epoch, which was empirical. An apple fell on somebody's head, and oh my God, gravity. And then we went into the theoretical epoch, which is, well, I'm going to sit on a light particle and do this thought experiment on what is going to happen, E equal to mc squared. And then we went into computational. We did high-performance computing. The Ken Kennedy Institute does a whole bunch of these things. I will submit to you that we are now in this new epoch of science where we are going to use AI in fundamentally different ways, and it's going to be super, super exciting. And so we have some incredibly exciting moonshots ahead of us. Some of it is going to be uncomfortably exciting. It's a term we use at Google to say that if you're not a little bit trepidation in terms of what you're doing, you're not aiming high enough. So whether it is systems, health, hardware, engineering, manufacturing, robotics, productivity, education, entertainment, every single one of this is going to change. And so with that, I want to conclude by kind of making a quick observation here. So we had the industrial revolution. We had the information revolution, so with the internet and mobile. We are in the beginning of an intelligence revolution. And like every prior revolution, it's going to have fundamentally transformative impact. It's going to have societal impact, it's going to have economic impact, it's going to have technology impact. So hopefully what you saw, we have systems for AI. I talked about unicorns and how we have really amazing opportunities. We have AI for systems with Centaurs and how we have some really amazing opportunities there as well. And we are entering this wild new world of cyborgs. And the common theme across all of that is this notion of co-design. Co-design across hardware and software, co-design across AI and humans, co-design across communities, co-design across academia and industry, co-design across policy, education, co-design across systems. So there is a whole bunch of stuff there. So with that, thank you for your time. I was going to end with JFK's video where he says, why does rice play Texas? But I will end with, how are you reinventing for the intelligence revolution? That's the scan code again, if anybody wants to ask questions. So once again, thank you. It's a privilege to be here.
Well, thank you so much, Partha. This was wonderful. We'll go to questions. Since you want to give the book to a student to ask questions, before I even start with the questions here, maybe we can open it up to the students only in the audience, and we see a question from the students. And before that, actually, I received a very serious question I wanted to ask you, which is, are you riding or chugging for alumni beer bike this Saturday? So I don't know.
Do I look like I'm capable of that?
Are there questions from the students? I think the students are afraid of having a book to read. They don't want to read.
There's
Okay.
Hi, thank you so much for the talk. I saw that you talked a lot about designing for agility and making sure that the hardware design is able to handle any different innovations that happen later in terms of actual model development. How do you handle the trade-off between that as well as creating really custom, like unicorns, like the trade-off between the unicorn side of things and the
Okay, so the question was, how do we trade off agility with customization, and are they fundamentally, is there a tension between those? So really good question. So you got your books, thank you. So I think there are two ways to look at this, right? So it turns out that agility is actually a good way to do customization, because one of the big challenges with customization is, how do I anticipate what's going to happen in the next 18 months? And if you're fast enough, you're allowed to make mistakes. You can kind of say like, hey, you know what, I'm going to build for Gemini 3, and then Gemini 4 is very different, I'm going to build for Gemini 4 as well. So that's one way to think about it. But the other way to think about it is, agility does not mean that you compromise fungibility as well. So when you looked at the agility slide, I said agile and fungible. And so thinking in terms of modular, interoperable systems helps with that as well. So then what you can do is you can take out one part and you can replace a cog in the wheel, and then things still work as well. Thank you.
You're a student?
Yes.
Okay, we'll allow one other question from students, and then I'll go to the questions here.
Thank you very much, Dean. I'm a current senior. My name is Michael. I'm thinking for your talk. My question is, because with AI, AI has been a very big part in software engineering already in all the big tech companies. And so implementation is getting much more cheaper, but instead how to become a credible verifier becomes a goal that I think we as junior developers really need to aim towards. So I am curious, like, what kind of suggestions you will have to a junior developer like me as I'm about to kickstart my software engineering career?
Yeah, every time I give this talk, I always get a question which is very politely worded about, AI is taking my job, what do I do? And it's a very fair question, and I think you articulated it really well. I think we need to think about what is fundamentally, computer science was not coding, right? And I often talk about Archimedes has this quote attributed to him, where he says, if you give me a fulcrum and a long enough lever, I will move the world. AI is the lever. The skills that you learn in computer science is the fulcrum. Without the fundamental skills in computer science, AI is just a stick. It's not a lever. And so going back to the question that you asked about, as AI does some of the mundane aspects of coding, the problem-solving aspects of computer science that teaches you are still very relevant. And so I would suggest, as the answer to the question about what advice, think about how do you do problem solving. Think about how do you deal with ambiguity. Think about how do you build judgment. Think about how do you build taste. Think about how do you do critical thinking. All those are very critical. And then second, when you do coding, you still have the rest of the workflow as well, and so start thinking about what you do there as well. And so personally, I think there's tons and tons of opportunity. So again, not to say that AI is not going to be transformational. I think there's going to be a lot of change. And my single biggest advice to all of you, and the advice I follow as well, is we are in for a period of change. And the only way you're going to know how to navigate the change is to get your hands dirty. So you need to start playing with things. Every Friday afternoon, I spend a couple of hours learning something, playing with this, and then you form your own opinion, and then you know how you're going to respond. Thank you.
Okay, we'll take a few questions of the ones that were submitted. One, I think, is one of the easier ones, Partha, is that how is Google, they asked it in terms of competition, but let's not worry about competition. How does Google work, let's say, against the models that are being developed by Meta, by Anthropic, by these companies as well? Like, how do you ensure that these models are always competitive?
So we make sure Google is the best model. So that's very simple. But I think the answer is a little bit more nuanced, right? So if you look at Google Cloud, we actually allow people to have access to Anthropic or to things. We are model agnostic in terms of what we do here as well. And again, I go back to industrial revolution, information revolution, intelligence revolution. When we are in a period of profound change, there's going to be innovation blooming all across the place. And so personally for me, I think it is super exciting that we have as a community, we have all of this innovation. And I think one of the things you realize is that each person kind of, this is very healthy competition where each person kind of brings the other person forward as well. So I personally welcome all the changes that are happening, and we kind of take that on as an interesting challenge to make sure that we are always ahead, and we are kind of, again, doing it in a responsible manner where we are advancing things too.
So speaking of responsible parts, and this is a bit harder question here, as you know, in the momentous strategic plan of the university, responsible AI features prominently. For our school, it features prominently. We actually just created Associate Dean for Technology and Responsibility. What is needed to ensure the ethical advancement of AI?
So to me, the first thing, again, I think is having your head in the sand and assuming AI is not going to change anything is the wrong answer. So the first thing I would like is all of us, whether you're technical, non-technical, I think it's important to realize that we are at a societal inflection point, and we need to participate in the conversation and influence the conversation. And that's at least something I personally have a lot of conviction on, is how do I make sure that the work I do is responsible and I'm thinking about it. So that's first number one. The second thing I think is responsibility has multiple stuff. It can be environmental responsibility, and I'm really excited by the work Rice does, for example. Some of the, I don't know how many of you look at some of the work done on water, and Rice is really nice. Energy, obviously, we are in the energy capital here, lots of really good work there. So there's a lot of stuff there. But when you go to some of the more deeper ethical questions there, I think this is, again, one of the places where Rice really shines, because we have this multiple schools. We have School of Engineering, but we also have liberal arts. We have business. And so, again, the reason I keep emphasizing co-design in my talk is really that you're going to have to kind of start thinking about looking across communities to bring the best of all of that to understand and how we want to solve that. So that is how I would look at it, is start thinking about it in a cross-disciplinary point of view, and there's a lot of lessons to be learned there.
Okay. Maybe one last question here. What jobs don't exist now that you think AI will create? New jobs, especially for the students who want to have these jobs?
I'm sure there is a job to repair the AI when it breaks. But honestly, I think, again, I go back to, I'm a student of history, right? And in many of these cases, it's hard to predict what is happening. I talked about AI native. If somebody had told me 10 years back there would be this TikTok video format where you would build videos for 30 seconds and I would spend 30 hours watching it nonstop, I would have said, oh, this is crazy. So there are going to be new jobs. It's very clear there are going to be new jobs. You already see this right now. Michael, I guess you asked, verification is getting very important, right? So now we are starting to say, when I have AI-generated code, how do I make sure that it is fine? So obviously, as each stage gets better, I think about it in terms of the learning cycle. So you go from data to information, information to knowledge, knowledge to wisdom, wisdom to impact to action, right? And so when you start thinking about that, at each stage, the next stage becomes kind of the new job that gets created. Going back to my example, when I'm overwhelmed with so many emails that summarize a lot of stuff there is a need to now kind of synthesize and curate it, and that becomes a new job. So you see historically this cycle where you kind of go up that cycle, and that becomes very important. So that is where I would look at. But again, I'm a student of history, and this is what I meant by going back to the liberal arts and understanding that history tells us what the answers are. Go back to your favorite period of change and look at what happened, and you'll get the answers to what are the new kinds of jobs there as well. Okay, thank you.
Thank you so much, Partha. Please join me in thanking Partha for this wonderful talk. This is a token from us for more school.
A backpack and an award. Thank you.
Thank you so much. Well, I do hope he retires that red backpack. I don't like it. But I hope you enjoyed the talk. I am sure if Raleigh Johnson was with us, he will be proud that we have such alumni of our school and such speakers here. So once again, I'm very grateful to the Raleigh Johnson family for this, and I do hope you all enjoyed this talk by Partha, and that you join us every year for such great talks here. Thank you so much all for coming. Please join us for a reception here with Partha outside. Thank you very much.